And the nice thing is today, hopefully the amplification is much better. You can hear me better in the back. Good, I see some thumbs up. Okay, we'll start with some announcements. So logistics, right? We've got quizzes and assignments in this class. Quiz 1 was wrapped up last week. Originally, I promised that there will be a quiz starting today until Thursday, but given that I gave an extension to programming assignment 1, let's move that window from Wednesday to Friday, right? So the quiz will launch at midnight, the coming midnight, and then stay open till 11:59 p.m. Friday, right? So by the time you turn in all programming assignment 1, that'll give you a Friday to tackle that if you're leaving it to Friday to tackle. Same format. It's going to be 2 45-minute tries, and the same idea, right? So you can experiment on iLab. You can use any resources you need to, but it is an individual, independent assignment. And of course, the most important thing is if you're experimenting on iLab and seeing what it gives you, the most important part is you need to be able to explain to yourself why you see what you see. Okay, but otherwise it should be a pretty familiar format compared to the last quiz. So the biggie, right? PA1 is going to be due Thursday evening, and today we'll spend some time talking about the second part of that, map chain mul. Given that this is one of your first semesters back in person, taking a computer science class, and especially this is a big class, right? I wanted to talk a little bit about, like, as a class, some of these questions, right? And I actually want you to take a couple of minutes to think, well, maybe like 30 seconds to think about this before we start really discussing it as a class, right? In the computer science classes that you've taken so far, so everybody's taken 111, 112, equivalents thereof, right? Why are the assignments hard? Right? Why do they take time? When you really boil it down, what is it about it that makes it so challenging? And I want you to think hard about this, right? And we'll talk about this as a class. And when you're stuck, like really, really stuck, like what are some strategies that you use to get unstuck? Think about like an assignment that you did in 112, and it seems super difficult at first. And what was it that got you moving again? I want you to think about that too. So give it, a few seconds, think about it, and then we'll start, we can raise hands and talk about it as a class. Yeah, so what is it that makes programming assignments so hard? I don't see a lot of hands, so I guess it's not that hard, right? Well, what is it that makes programming assignments so difficult? Just in general. In general. Well, okay, so somebody has jumped the gun, but yeah, sure, go ahead.
Knowing where to start, but it's like approach and there might be an easier way to do it.
Okay, so I'm hearing many ways to tackle the problem, and once you solve it, you realize maybe there was an even easier way. So there's a kind of like, well, maybe I'm not going about it the right way. This might be the hard approach, but here we go anyway. Okay. Good answer. Yeah, over here. Okay, so you're working on your solution and you're missing some parameter and you're trying to take account into the thing you missed, and it's hard to break out of the original thinking, right? So certainly that something could have happened with the sort jobs or the greedy algorithm this time around, right? You write a program, it gets most of the cases, but you forgot to take into some important piece of the information, and now you don't know how to fix it efficiently. Yeah, that's another challenge. Yep. Yeah, over there, back. Yeah, you. Okay, so you have if you're not familiar with the programming language, you know what you want to do, but you can't translate it into the code that you want. Yeah, that's a big reason. Anything else? Any kind of more unconventional reasons over here? Yeah, you run out of time, get stuck, and run out of time. That's a possibility. Okay, well, this is eating into our like actual work time now, but these are all real reasons, right? And the point I want to bring this up is, all your classmates are going through the same challenges, right? So when you're stuck, it's not just that you're stuck. Probably there's somebody else that's similarly stuck and facing the same kind of challenges, right? So in the classes you've taken before, when you got stuck, what were good strategies to get unstuck? Yeah, over there in the corner, not the corner, but the side. Yeah, you. Yeah, so illustrate what you're trying to do, right? So forget the code, forget the program, forget the compiler, forget running it, forget the test cases. Take out pen and paper and draw out what you're trying to do. Right? A lot of data structures work. You need to work through a picture to really understand what's going on. Right? And this is true. This is why everybody has whiteboards. You go to some programmer's cave, they have whiteboards everywhere because you always want to pull out pen and paper to illustrate things. Any other strategies? Yeah. Yeah, so explaining what you're trying to do to somebody who doesn't know what you're doing, right? Talking through your code can help a lot. And this is something that we try to do with Piazza, right? While you're not allowed to wholesale show what your code is, if you can explain what you're trying to do on Piazza, or via in class here, or during office hours or citation, right? The process of trying to explain what you're trying to do is a huge mental help to structure your thoughts. Okay. What are some resources? Right, so those are strategies, work strategies, but there are also resources, right? So what are things that you can turn to? Yeah, again. Yeah, so I'm glad you mentioned cave, right? So this is kind of what I wanted to ask. So how many of you are familiar with the cave? Right, so not everybody. So can somebody explain what is the cave and what goes on at the cave? Purple shirt. Yeah, so these are so at the cave you'll have students who took the same class, a semester ago, and they want to be there to help you, right? And I think the cave has long hours, and it's pretty flexible, right? So even outside of the resources we have in this class, it's like you always find somebody who's been through the same stuff at the cave. Any other resources? Yeah, red shirt. Stack Overflow, right? So Stack Overflow is kind of like Piazza for the real world in some sense, right? You may your mileage may vary, right? But there you'll have some classic questions in computer science, and the key thing is Stack Overflow is user rated, right? So it's peer reviewed, right? So a good answer is likely to get some more votes, and so you can filter out what are the good answers via Stack Overflow. Yeah. Okay. So I think that was a helpful thing, right? So I've been hearing comments like, yeah, we don't know where to start, and so forth, right? I think these are some high-level ideas to help get unstuck. Here's a few things I kind of want to say, right? So I think these are some underappreciated facts about programming that the classroom environment here doesn't really portray. So I think one important lesson as you become more proficient in programming is coding deliberately is important, right? So this is something I see kind of during office hours and on Piazza, right? I see code that is kind of a little bit based off of trial and error. And trial and error is a very difficult approach to programming, right? So what I'm trying to say here is it's helpful to have a plan, know what you're trying to do in the code. And then for the code that you do have, you have to read and really understand it. Don't make assumptions about it. If the provided code already doesn't make much sense, you're not going to be able to base any new code off of code that you don't fully understand what's going on. Right? And this other part, test assumptions, is important, right? So suppose that you're stuck somewhere and you're trying to debug some line. Well, one approach is you want to really investigate what's going on. Are the things that you assume what's going on in your program really true? So getting some printf statements, some insight on your code is helpful. Another is less code is better and more likely to be correct, right? So if you're going off some wild tangent and getting hundreds and hundreds of lines of code to fix some problem, it's probably a good time to take a step back, right? If you were to start over with the ideas that you have now, you'll likely, start from a cleaner slate and build up the right code now that you're giving it a second try. Another thing, reading code is important. This is something that's a little bit underappreciated in classroom setting too, right? We've placed so much emphasis on you have to write this program and tackle this next assignment, and here's the next part, and so forth. But if you really ask people who practice computer science and are programmers and use computer science in the real world, most of their time is when they're dealing with code, most of that time is spent reading code and not writing code. The actual step of sitting down and creating new code, that's a tiny sliver of the whole software cycle, right? A lot of time is spent reading code, maintaining code, debugging code, testing code, documenting code, and the actual writing portion is a very small portion. So even if it seems like, okay, I'm spending too much time reading the provided code, realize that that's an essential part of programming. And the last part here is, in the real world, programming assignments, programming projects are team-based. And so for these intro and intermediate courses, we don't really have team-based assignments. The programming assignments are individual. You're not allowed to see each other's code. But still, we try to create a kind of environment that's collaborative via something like Piazza, right? If we have a difficult assignment and as a class, we work through all the details on Piazza such that after you read all the Piazza posts about it, it becomes obvious how to tackle it, and that's fine, right? I'm happy that everybody can do the assignment if, as a team, people are working it out on Piazza. So those are just some thoughts I wanted to share. Okay, any questions before we move from kind of these abstract things to the real assignments? Sounds good? All right, so all of this is very abstract. Let's talk about the dynamic programming problem. Right, so what I'm going to do now is, before we go into the code, let's talk about what is this program, right? So how many of you had a solid chance to try programming dynamic programming? Oh, sorry, not dynamic programming, but the matrix chain multiplication problem. So yeah, a third. Okay. So the main things that we want to learn in this assignment part, matrix chain multiplication, is this is a very nice review of recursion. And recursion is one of those really tricky things that we learn a little bit in 111, 112, but to use it in a program and an assignment, it's always a little bit tricky, right? So this is a very nice chance to review that. One of the things that we're trying to learn in C is how to use arrays and pointers, and this will demonstrate how to use arrays and pointers to subset your arrays, right? You have a long array. I just want some chunk of it, and we can use pointer arithmetic to do that. And some other concepts, right? You pass by reference, returning results. And another nice thing is this is a new algorithm. It's pretty cool, right? So there's a kind of nice aspect, which is everybody is starting fresh on this particular algorithm, right? And I'll tell the class right now, right? So I've opened some of the submissions that have been already submitted, and not everybody is doing it exactly the right way or using the kind of the full approach here, right? So you can program it in a way that you pass the auto grader, but the full algorithm implementation, that's what we'll be talking about today. So even if you've turned it in, you got the auto grader gives you 100%. There's something to learn from talking about it today. Okay, so the task is you're multiplying matrices, right? So multiplying matrices, you've got two matrices, A and B. They have dimensions, right? So matrix A is L times M. Matrix B is M times N, right? And so a key thing is the inner dimensions of the two matrices have to match. So does this make sense? Should I draw this out a little bit? So we've got two matrices, right? A, B. A is L rows tall and M columns wide. And when you multiply these two together, the column dimensions of A have to match the row dimensions of B, right? So M equals M, and then you have a third dimension, N. What's the dimensions of the multiplied result? L by N, right? So suppose this equals C, it will be L rows tall, N columns wide. Makes sense, right? And how do you multiply matrices again, right? So this is actually not so important right now because we're not going to be talking about the actual multiplication step. But just as a review, how do you multiply these? Row of the first, column of the second, right? So that's the rule. Row of the first, column of the second. So if I had an element here in the way upper left corner, where does this come from? Dot product of the first row in A and the first column in B. So you've got a vector here, you've got a vector here. Dot product, inner product of the two vectors gives you this element here. Make sense? So to multiply these two matrices together, how many operations do you need? L, M, N. So this is the number of multiplications you need to do this. And that's the answer we'll go by for this class, right? Actually, there's a little subtlety to that. There are more advanced algorithms called Strasson's algorithm that can do this in even fewer multiplications, but that's kind of a well-kept secret, and we don't talk about that in this class, right? It's a cool thing, and actually an interesting thing is, in general, computer scientists don't know what is the lowest bound on matrix multiplication. So we don't actually know how few multiplications you need in the kind of the most extreme algorithm sense. Okay, but anyway, this is the number of multipliers we'll use in this class. Okay, so good, so far so good. Check the chat box. Okay, so now the tricky thing is if you got multiple matrices, right? So you have three matrices now, A, B, and C. depending on how you parenthesize the operations, you can actually get away with different number of multiplications. Right? So can somebody tell me what's the difference between the first case and the second case here? I've got three matrices. A is 1 by 2. B is 2 by 1. C is 1 by 2. All of this is good because you see the inner dimensions all match, right? So the number of columns of A matches the number of rows of B. The number of columns of B matches the number of rows, the rows of C, right? And okay, so now what's the difference between the first approach and the second approach? Yeah, so this is about the parenthesization, right? Which is we can do different orders of operation. We can multiply B and C together first in this case, versus here we can multiply A and B together first. And even though both of these get at the exact same result, right? So both of them symbolically will get to this final result. It's a 1 by 2, a single row matrix. The number of multiplications that you needed in between can be very different. Here, you need 8 multiplications in the first case, and you only need 4 multiplications in the second case. Does this make sense? Some nods. Question here. How is it 4 multiplications in the second case? Okay, so let's count them, right? So first we had to multiply A and B, right? So we had to multiply this term that I'm circling with the cursor. Here's 1 multiply, 2 multiplies, and then we have 3 multiplies and 4 multiplies. Right, so you can see that this becomes a single scalar after this term. So here, the scalar times C00, that's 1 multiply here. And the scalar overall multiplied C01 is another multiply. So 2 plus 2. That's right. Yeah. So that's a good point, right? The particular way I wrote this makes it hard to see that this is, you can get away with this with two multiplies. Good comment. Okay, so this illustrates the interesting part, right? So we want to find what's the optimum number of multiplications to solve this. And the class of algorithms to tackle this kind of problem is called dynamic programming, right? So it's a class of algorithms that has some common traits to it. So the general idea is you want to do a divide and conquer approach. And then the second idea is you break the problems into smaller and smaller pieces, and the answer from the smaller pieces informs your decision for the bigger whole. Right? So these are just it's just kind of a loose description of what dynamic programming approach means. And this is probably not so much of the algorithm that we've studied in 112, but actually everybody here is equipped to understand the beauty of it and try programming it. And that's why I picked this algorithm class. And also, it's an excellent way to exercise our understanding of arrays and pointers. Right. In the assignment description, I talked about how this type of algorithm shows up in a bunch of places in computer science, like computational genomics, matching strings. All of these have applications of dynamic programming. Okay, so what we'll do now is, so what's the idea here? First, let's actually work through a more complicated case, right? So we have now 4 matrices, A, B, C, and D. And ultimately, what we're trying to do is we're trying to figure out within all of these, what's the minimum cost out of all 5 of these options which one has the least cost, right? And we're going to structure this figuring out via recursion to get at all the cases. So how do we use recursion? Well, so we use recursion in this way. First, we have this whole problem, A, B, C, and D. And we want to figure out, okay, well, here you only have one choice on where to split it, right? So you only have to pick one place to split this whole string. So there's three places you can do this split, right? You can do A multiplied by BCD altogether. This is one choice, right? So this is the first choice because we're putting the split right after the A, the first place you can split it. Then you can split it in the second place, right? So you split it now after the B. So what you're going to do now is you're going to find AB first, and then CD, and then multiply these two together. This is the second approach. And then the third approach is we're going to do ABC together, and then multiply that against D. So this is the third place to split it after the C. And this is the third approach, and that's it. So here, if you're trying to split A, B, C, D into two pieces, here are your three options. Now, here's the thing, though. At first glance, can you tell me how many multiplications this approach is going to take? A times BCD altogether? Well, we don't know, right? Because this BCD multiplication, that itself is also a matrix chain multiplication problem. And so we've only just decomposed the problem into a smaller problem, and now we have to solve that subproblem. So the idea here is, okay, we want to then figure out how many splits what's the best way to split BCD. So that's why we do another decomposition, right? So this case, A times BCD altogether, this splits into these two cases here. And for these, now the problem is small enough, right? So this problem of finding CD, this problem of finding BC, it's small enough, it's the base case. It's the bottommost case that we can trivially figure out what the cost of that is. Okay, so this is a little bit abstract, and now we'll work through a full example of this. But any questions so far? Is it clear kind of where I'm trying to go with this? Yeah, question. Yeah, so the question is about this first column here, right? So we're focusing here. The question is, when I do this split, what does this mean, right? So when I do the split, I'm just looking at, given a place, I've got A, B, C, D. I can split it here, that's choice one. I can split it here, that's choice two. I can split it here, that's choice three. Right? And when I split here, that means I'm going to do this first, put a big parentheses around that, find this, and then multiply by D. Yeah, so it's the same process, right? So now, suppose I want to investigate this case some more. Well, then I have to figure out what's the way to split A, B, C. So I basically take this case, and I consider, well, I've got A, B, C, A, B, C. I can split it here. That's case one. I can split it here. That's case two. Right, so this leads to two different ways to partition this, which means that this case here, there's actually two subcases on how to split it. Purple shirt. Yeah, so I think the question before getting to actually doing the multiplication, matrix multiplication, the idea is here, okay, so what does it mean that I've done this parenthesization, right? So now I can say this equals S times D, and now you've only got two matrices. to multiply against each other. So the question is, what's the optimal way to split S, where S equals ABC? Okay, so what I'll do now is I'm going to go to dynamic programming. This is our class source code, right? I'm going to open test case 3 because it's just about the right size. And we'll work through test case 3 by hand. So this text file here, what it says is there's 4 matrices. If I zoom in. So this test case file is saying that we've got 4 matrices, A, B, C, D, 3 by 3, 3 by 4, 4 by 6, and 6 by 4. So what we'll do now is we're going to consider all the cases, right? So like we said before, the first approach is A, B, C, D all together. Right, so A is going to be a 3 by 3 matrix. This, what's the dimensions of BCD going to be? Yeah, 3 by 4, right? So this should clarify things now, right? So BCD, once you've done this multiplication, however, how you do that, the dimensions of this will be 3 by 4. Right, so this will be a 3 by 4 multiplication. That's option 1. You have more colors here? No, it's just white. Okay. Option 2, AB, C, D. So what's the dimensions of AB? Yep, 3 by 4. And CD? 4 by 4. Good. Case 3. A, B, C all together by D. What's the dimensions of ABC? 3 by 6. And D itself is 6 by 4. Okay, so this is the first level of decomposition, right? And so given this, we still don't know what's the best one, right? So I have all this, right? I can say, okay, this level of decomposition, what's the number of multiplies needed? Right? So we said that the number of multiplies needed is L times M, the M dimensions match here, times N, LMN. Right? So 3 times 4 equals, let me give a, I don't know, P. Let's give me a variable name, X. So X is the cost here. So X is going to be, oh, like X, looks like times. Let's say Y. 3 times 3 times 4 is 36. Plus, how much is the cost of multiplying this? Well, we don't know yet. Right, so we'll put a pause on that. We know that at this level, the cost of this is going to be at least 36 plus something else. Does this make sense what I'm doing here? Right, so all I've told you is just to multiply A with BCD, there's going to be 36 multiplies. This is the cost of this operation. And plus, whatever is the best way to do this. And we don't know that yet. So we'll put that aside. We'll consider that later. What's the cost of this? L times M times N, right? So 3 times 4 times 4 is 48. Plus what? Plus, well, what's the cost of finding this and this? And we don't know that yet. We'll leave that, put that aside. How about this one here? What's the cost of finding this? Three times 6 times 4. 72. Plus something, right? We still don't know what's the cost of finding ABC itself. Right, so this is one level of recursion, right? So far we found that the minimum cost of each of these approaches is going to be 36, 48, and 72 each. But specifically how much it's going to be in total, we don't know yet because we need to recurse. Okay, so now let's split this up into groups here. I'll put a divider line here. Now we have to figure out what's the cost of BCD, right? BCD, the first approach is to put the divider here after B, the parentheses around that. And then B, C times D. What's the cost of this? 96? How do we get 96? So 3 times 4, dimension of CD is 4 by 4. All right, so 3 times 4 times 4 is 48. Plus something. Right, so we still have to do C times D. Right, is this clear what's going on here? Now, what's the cost of finding CD? 4 times 6 times 4. 24 times 4, 96. Let me check the work on this. Make sense? Right, so what does this say, right? So the total cost of this approach is going to be 36 plus 48 plus 96, whatever that is. What is it? 180? Okay. Okay. Do we work through all the rest of the 4 cases? Yes, no, lost, boring. Yes, keep going. All right, let's keep going. All right, so what's the cost of this? What's the dimensions of BC? 3 by 6. Dimensions of D, 6 by 4. So the cost of doing this multiplication, BC altogether times D, 3 times 4 times 6, 72. Is somebody checking the work on me here, or am I just going, okay, I see a thumbs up, good. So then the last piece is the cost of BC, right? So BC itself is 3 times 4 times 6, 72, plus the original cost here, 36, whatever that is, 180. Do you understand where this 36 is coming from? 36 here, this 36 and this 36 comes from the original decomposition, right? So we already, at the first level, figured out if you were to go about this approach, just to do this, you have 36, 36 multiplications you have to do there. Okay, let's keep going, right? So here we have the cost of AB, which is 3 times 3 times 4, 3 times 3 times 4 equals 36. CD is 4 times 6 times 4, 36, plus the original cost, 48. Whatever that is. But again, 180. Two more. Keep going, or you get the idea. Lost, confused? Keep going? Okay, 2 more rows, right? So now we have to find the cost of A, B, and C. So A, B, C, again, 2 ways to approach it. Right, so we can put the divider in the first possible position, or put it in the second possible position, like that. The cost of this multiplication altogether, A times BC altogether, is going to be 3 times 3 times 6, 54, plus cost of finding BC itself. Right, so 3 times 4 times 6, 72, plus the original cost of 72. What's that equal to? $72 plus 54 plus 72. $198. So the last one, last row, right? So the cost of AB altogether times C, 3 times 4 times 6. 72 plus cost of finding AB itself, 3 times 3 times 4, 36, plus the original cost here, 72. Right, so this is going to be 180. Right, so this approach here, so in total, now that we've done all the grunt work, in total, the cost of this, the lowest option is 180. Make sense? Unclear? Right, so we can go and look at the answers directory. And hopefully, the answer to answer 3 is 180. Right, so this is where this 180 is coming from. Okay, very good. So now let's actually talk about like the source code, right? So how will we go about finding what's the cost of this? So let's go to dynamicProgramming.c. And I think here I'm going to go back to the podium now. Okay, so I talked about how the matrix chain multiplication problem, you have 2 example codes that feed into it, right? So the dynamicProgramming.c just does this. It just does this finding the cost, and it doesn't actually do the matrix multiplication. And on the other hand, there's the matrix multiplication, the matmul source code that gives you an example of doing matrix multiplication. Right? Makes sense? So the way that this code is working is it uses recursion. Right? So once we open this code, where should we take a look first? Like, if you open a big source code like this, where's the first place you go take a look at to try understanding? Heard main method? Okay, let's go to main method. Right? So it seems like the main method here is doing a few things. There's the standard, we're going to open the file. Right, so up to this point, we've opened the file. Then we have these 2 arrays. One is for row sizes, and the other is for column sizes. And both of these are going to be integer arrays. Right, they're of type unsigned integer star. And we've already figured out how many matrices there are in total, right? That was the first parameter we brought in here. And so now we have two arrays, one of row sizes, one of column sizes. And the next piece here is we then go ahead and read the rest of the file and load in all of the row dimensions and the column dimensions. All good so far? Right, so now we have, after this point, we have two arrays, row and col, right? So in this example here, what would the row array look like? Do I call it row dim? Row sizes. Row and col sizes. This is an array. This is an array. How many elements in the array? 4. And what are the row sizes? Row sizes are going to be 3, 3, 4, 6. Column sizes? 3, 4, 6, 4. Make sense? Okay, so here after line 75, we've done that. So now, the rest is not much to see, right? So that's the main method. The rest is just to clean up after ourselves. After you've done the work here, the rest just frees up the arrays that we allocated, closes the file pointer, and we're done. So the bulk of the work is happening here, whatever this is, the call to cost. So let's go look at cost. Right, so we'll look at cost, and cost takes 3 parameters, the number of matrices, and the row and column dimensions. And the first thing to know about cost is, well, somehow it calls itself. So you'll see that cost, inside itself, it calls cost in of itself. Right, so we can already tell that this is a recursive code pattern. And what is it considered to be the base case here? Right, so all recursion, what are the essential ingredients of recursion? Base case, and what do we call the other one? Base case, what's the opposite of base case? Inductive hypothesis, okay, 2 big words. Yeah, we call it induction case, maybe, or the recursive case, maybe. Right, so we have the base case, which is the smallest kernel that we trivially know how to solve. And then there's the inductive case, which is more complex, but we rely on the trivial approach to show it. How is that playing a role here? Right, so how is this recursive pattern playing a role in what we just did here? Yeah, purple shirt. Yeah, so we're taking a big problem, turning it into a small problem. Maybe I'll ask another question, right? So in what we just did here, what's the base case? A few more hands. I don't want to call somebody who hasn't talked in class yet. Green shirt. Yeah, so right to it, right? So the base case here is, if I have just one matrix, I gave you a matrix, what's the cost of finding B? Well, B is a matrix, right? There's no multiplication to be done. And so by definition, its cost is 0. Right, so this is one way to think about what the base case here is. And I'll tell you this, right? So when I was preparing this code, I originally didn't use that as a base case. What would have been another potential idea for a base case? Right, so that's a good answer. That's a nice, clean way to do it. What else would be a good candidate for a base case? Yeah, just two, right? So that's another idea. Maybe as a base case, you can just say that, well, the base case is when you hit just two matrices you want to multiply together, then you know L, M, and N all fully, and we can return the cost is L times M times N. Right? So those are two ideas for what the base case is. Here in this code here, we're going with the interesting base case, right? Trivially, if there's just one matrix, the cost is 0. And we've actually tucked the L times M times N away into the recursive case, right? So what I'm saying is the case where you're multiplying two matrices together, that's a special case of the recursive case. Right? So you can kind of factor the code so that when you have two matrices, it gets captured here in the else clause. Okay, makes sense? Unclear? Yeah. The other code does the actual multiplication, or what does this one do? What does this source code do? Right, so this source code here is dynamicProgramming.c, and all it does is it tells you the cost. Right, so if you look at the directory structure, I'm in the directory dynamic programming, and it takes as input a file that looks like this. 4 matrices, these are their dimensions. It doesn't actually say what the matrices are, right? So this is just metadata about the matrices, the dimensions. And the result of the program, the expected output, is one number, which is the number of multiplies needed. And so this 180, we got at this 180 from our worked example here. Okay, so now let's zoom into the inductive case, right? So the induction step of, well, the rest of it all. So the first thing we have to figure out is how many things are we comparing, right? So we worked through this example. Suppose I gave you matrices BCD. How many possible ways are there to split? 2, right? So we can split it here, treat the rest as one chunk, or we could split it here and treat the rest as one chunk. So already we know that the number of cases that you want to compare each time is the number of matrices minus 1. And we can check that, right? So back here, when we had 4 matrices, A, B, C, D, how many options were there? Well, there's 3 places we can split, right? So when you have 4 matrices, 4 minus 1, 3 options to split. And this makes sense, right? Because the options to split are, wherever between the matrices are. So however many gaps there are, that's the number of places you can choose from splitting. So this code here, what it's doing is, all right, so we know how many choices we're trying to split on. And now we have a cost, right? So we create an array of that many options of splitting. And you'll notice here that I'm actually doing a variable length array here, right? So this is C syntax that we don't really encourage, I guess, in this class. But here you can create an array with a variable number of elements. It works. And if we zoom all the way down here, right? So somewhere in here, it's going to do some work. Somehow in here, it's going to fill in that matrix. And down here, this code pattern here, what is this doing? Right, so the part I highlighted. Yeah. Yeah, right. So what I've highlighted there, it's basically finding the minimum element of an array. I've given you an array. Here, let's look at this case. We're trying to divide BCD, right? So I'm looking at this chunk here. No, don't look at that chunk. That's a bad example. Let's look at this chunk here. Here, right? So I've given you A, B, C, and I want to know between these two options, what's the best approach? Well, I've populated the matrix, the array with 198 and 180, and I'm just going to iterate through that array and select the lowest element, right? So the minimum element is 180, and it just compares the elements in there to see, well, is there anything that beats 180? Finding the minimum element of an array. Okay, good, right? So then once you found that, it returns that. So far I've told you everything in this code except for the critical piece here. So the critical piece here highlighted, what this is doing is it's actually doing this multiplication, right? So I want to find what's the cost of this multiply and what's the cost of this multiply. And so I gather some data, right? So to make the code more clear, I collect, well, what is the L, M, and N that we see in that moment, right? So the L is the row dimension of the first matrix. The M is going to be the column dimension at the place we split. And N is going to be the column dimension of the very last element. Right, so this is actually pretty tricky here. So I want you to stare at it a little bit and yeah, explain it one more time, right? Okay. So let's use a concrete example here. So we got these row sizes, and we've got these row sizes. And right now, this is what happens when we have matrices A, B, C, and D. This loop here, what's the num possible split, given that we're considering this problem? Num possible splits equals 3, right? 1, 2, 3, 3 places. So we have an array. Num possible splits equals, here's an array, 3 elements. We're going to fill this in. So filling in the first element here, which means we're going to consider this case, right? What's the cost of this multiply? Well, the cost of this multiply is going to be dimensions of A, 3, 3, times BCD altogether. What's the dimensions of BCD? 3, 4. Right? And double check here. That's what we said here, 3, 4. So where do we get all these? 3, 3, 4. Well, this 3 is the first element of the row array, right? So the row dimensions of the first matrix. So that's where this comes from. So that's where we get L here. L equals 3. This makes sense or no? Maybe. Okay. M. What's M? 3, but where does that 3 come from? Yeah, Hoodie? Yeah, so this 3, this M dimension is either, you can get it from 2 places, right? You can either say it's the, okay, well, what we should do is, I should say, right now, we're indexing into this, and we're going to say split equals 0, right? So 0 encodes the first place to split, and this 0 means I'm going to split it here. So there's a little bit of offsetting going on. So split at 0 means put it here. And so you can get the row sizes M either from this element or from this element here. right? So because you can get it from either place, we actually say, okay, let's assert that, right? So these two values should be the same, otherwise something has gone wrong, right? So this is just a sanity check. And so we get M from column sizes, the first element of column size, and N, well, N is the column dimensions of this whole thing altogether, right? So it comes from the very last element here, column size is last element. So we've gathered this information from the appropriate places. And the way we go about this is not from abstract, right? So we work through a detailed example to figure out, well, if we were working through this pen and paper in a small example, how would you get this information, L, M, N dimensions? Okay, so now what we're going to do next is now the cost, right? So the cost overall, the cost that we would place in here comes from three components, right? So this cost here comes from the cost of finding A, the cost of finding BCD, and the cost of combining all this together, A times BCD altogether. So you'll see that the middle case here, right? So the final multiply BCD versus A, well, that's L times M times N. And then you have the two recursive cases. So the recursive cases here are what's the cost of finding everything to the left of the split, and what's the cost of finding everything to the right of the split. Okay. Yeah, purple shirt. Yeah, good question, right? So now we actually have to take a very close look at why I wrote these two lines the way I did here. Right, so the first one is easier. The second one is a little bit more tricky, but it's the same idea. Right, so what this is trying to do here is we've already figured out, or we've established, right? If you have these two submatrices, A on one side, BCD on the other, this multiply here is going to be L times M times N. That's fine. Now, we don't know what the cost of the left subchain is, which is what's the cost of A? And what's the cost of that? Well, this is a subproblem, right? We're going to take our input matrices and give it to a recursive call and ask the recursive call to tell us what's the cost of finding A, right? So what's the dimensions of this? We've split it at 0. The dimensions of the left subchain is going to be just 1, right? To the left of the split, there's 1 element. So that's why we say the subproblem is going to have a dimension size of split plus 1. And you can consider more cases, right? So suppose that split equals 1, we're splitting it here. The left subchain is going to be 1 plus 1 equals 2. And the subproblems take pieces of our rows, right? So we're going to give the subproblem subsets of this problem here. And instead of telling the subproblem to look at the whole matrix, we're going to say, here's your matrix. It starts at here, starts in the same place. But this time around, I would like you to only consider a subproblem that has 1 element in the array. Right? So what's the high level idea here? Well, what's happening in this line is we're giving the call to cost pointers to these same arrays as before. But then by changing the first argument, what's the first argument? First argument is matrix count. By making this first argument smaller, the subproblem is going to look at a smaller subproblem. So it's just only going to consider a single matrix of 3 by 3. So this explains how the first call to cost works. Okay, so what's the point of this other call? The point of this second call? It's doing it on the other side. Exactly, right? So it's going to do the rest, right? So I've split this problem. We've got A on one side, and we still have the other side, the right subchain. And what's the dimensions of the right subchain? The original problem minus however much we've delegated to the left subchain. So we said that this size is split plus 1. So now the total cost of this is going to be the original problem size minus split minus 1. Right? So in this case here, originally was 4. We're going to split away 1. And so the subproblem here is going to be size 3. So this explains this parameter here. And we're going to delegate this size 3 problem off. And what are its inputs? Same thing, right? So we have our row dimensions, column dimensions, and we're going to offset it, right? So we're going to offset it so that we split off as a subproblem this piece here, this piece here. Good, confusing, and clear? Is there something I can clarify that might just like get it to click? Yeah. Does the program know the cost of A times BCD? Good question, right? So does the program know, when does the program know if, the various costs, right? So what's the order of evaluation here? If you think about this code, what actually ends up being calculated very first? Well, it's a kind of a depth first traversal, right? You call cost on the whole problem, which then keeps calling cost until it breaks it down into a trivial case. So the very first thing it's going to figure out is, well, A has cost 0. Then it starts backing out, right? So then what's the next thing it calculates? The next thing it calculates is in here. LMN, it's going to know that A and BCD altogether is going to be cost 3 times 3 times 4. So it's going to figure out this thing next. It's going to figure out that A times BCD is going to be at least cost 36. Plus what? Well, it doesn't know yet, right? So it doesn't know what's the total cost of BCD. And so that's why it recurses. It's going to send as a subproblem the subset BCD into another call to cost. And ask that call to cost, well, what do you think is going to be the minimum of BCD? And BCD, well, it's just yet another, it's exactly the same problem format, right? So just same code, different inputs, same thing, it'll consider BCD, look at these two options, and return the minimum of these two. Good question. Yeah. So say that one more time. Just I lost track. Mm-hmm. Exactly, right? So what is what I highlight here? Row plus split plus 1. What does this mean, right? So row size this is an array. So what does it mean to add an array to some numbers here? Well, we talked about how arrays, the name of an array secretly is a pointer to the beginning of the array. And so when we do pointer arithmetic like this, we're saying, okay, instead of starting the array at the beginning of row sizes, start your array slightly later, start slightly farther along. So that what I'm saying here, row sizes, instead of starting at the 0th element, start instead at the first element, which is going to be split plus 1. So by saying row sizes plus split plus 1, we start the subproblem here. Okay. So anything else about the cost finding aspect of this? Okay, so how do we actually use this to do the assignment, right? So all of this is the recursive code pattern of doing matrix multiplication, right? So what's the key thing that we need to extract from this? Right? So suppose I now give you the actual whole matrices, and from this calculation here, I say that this is the best approach. Well, how do we know that we're going to do the matrix multiplication by splitting down here? Where is that information getting encoded? Yeah, so the proposal there is maybe use this function to return the split value. Well, could we do that? Not really, right? So right now, the function signature of this is going to return the cost. And because this is a recursive code, we don't really want to make this return something else. But you could just copy and paste this code, right? So you could take this code, the place where it's encoding where the split is, we could do something like this, right? So we can say unsigned int best split equals starts at 0. And if you have found a minimum case here, right? So the cost that you found defeats is less than the minimum cost you found. And you can say best split equals split. Right? So after you found the minimum element here, this will give you the best place to do the splitting. Yeah. So the question is, would you just split at one place? Would you split at multiple places? Yeah, okay, so here's the key thing though, right? So the question is, okay, well, what does this tell you about multiple places to split? And the answer to that is, well, there is only one place to split at any given level of recursion. So at this level of recursion, we only consider one place to split. Exactly what BCD is, that's somebody else's problem. So at every level of recursion, there is just one best place to split. There may be equal valued places to split, right? So we could say 180 is 180 and 180, these are all the same, equally good. But still among them, you just pick one. How would you return best split? You don't have to return it, right? So you could integrate your matrix chain multiplication code with this cost function and use the split that you have here while you have it to do the matrix multiplication. Yeah. What does the number mean? So if it prints out 2, what does it mean? Right, so let's say where would it print out 2? Right, so suppose it printed out 2 here, right? So printing out 2 means among these places to split, 0, 1, and 2. Filling at 2, if best split equals 2, it means pick this approach, do this approach, right? Whereas if best split equals 1, it would mean this approach. If best split equals 0, it means this approach. Why best split equals, so why, when we say best split equals 1, why does it mean this approach? Right, so we've said split equals 0. Split equals 0 is the first possible split, which means this approach. The second place, or index 1, if split equals 1, it means split it over here, the second possible location, first and second possible location, which means split it here. And when you split it here, it means you've got AB times CD over here. That's how that's encoding it. Yeah, one more question over here. Yeah. So we'll do some a little bit of live coding, right? So 2 minutes of live coding here, or 2 minutes of like exactly how would you use this. So suppose now instead of having a cost function, suppose I've having a cost function, we just copy and paste that whole thing. This time around, this function is now going to be called matrix chain multiplication. What should be the signature of matrix chain mul? You need all the same information as before, right? But this time around, you actually have to provide the matrices. So what are matrices? What's a 2D matrix? Star, star? But this is multiple matrices, right? Plural matrices. So we add another layer because this is an array of matrices, multiple matrices. Each pointer points to a whole 2D array that you've loaded. What should this return? We would want it to return the product, right? What's the type of the product? What's the type of a matrix? What is a matrix product? Another matrix. And how would you describe that as a C data type? In double star? Right, so this is kind of the general recursive function signature that you want to flesh out. Right, all of this code is still useful. Like the rest of the cost code that we wrote before still tells you what the cost is, but now this time around, you have figured out what the best split is. So after that, you have another call to, how many calls to matrix chain mul here? Right? What am I trying to do here? Right, so paraphrase that, left product based on the best split, right product based on best split, and to find those left products and right products, well, this is just another call to itself, another call to matrix chain multiplication. right? Okay, all that is fine. And then you still have to multiply the things together, right? So return what? Well, return, somehow you have to multiply the left product and the right product and then return that. Right, so you start to see how this is, if you take the matmul code and put it into here and make it a recursive call, that will solve the overall problem. Okay, so our time is up. I'll stick around to keep taking questions. Otherwise, good luck. Bye. Hi.
I have a quick question. I mean, I've only done the first part of the assignment so far. I've only done greedy. So, like maybe there's something I don't know about this, but when we multiply out for the products that we have to return, like the final matrix, should we go in the efficient order, like with best split, like?
Well, you should, right? So that's the whole purpose of